Hello everyone, my name is Gaurav Gupta and today we will make a machine learning project for satellite image classification. This dataset is available on Kaggle and I will link the link for the dataset in description. Also you will see the link of this notebook in the description. So if you like the notebook, please support me on Kaggle, and if you like this video, please do like, share and subscribe the video. So let's jump into it. So we are dealing with satellite image classification. First, we will look at the data. You can see we have one data folder which has four directories: cloudy, desert, green area, and water. You can see each of them has approximately 1,000 files. These files are actually images. So let me show you one. Here you can see. Let me full screen it. See, this is a cloudy image. It is actually satellite image, so it might not look that good, but yeah, these are the images we are dealing with, like in desert. So these are the images. Let me close it. So we will code a neural network or a deep learning model for the classification. So let's start building our model. To build the model, we first need to split this data into two directories: training and testing. So I will be making those directories in this slash kaggle slash working. Then we will make the subdirectories same as cloudy, desert, green area and water, and then we will import all the images in our code and train. So let's start with the code. First we will import the necessary libraries. So first we will import numpy as np, import matplotlib dot pyplot as plt. These two will be used for image for displaying the image, so that we can look in the code that what are the images we are dealing with. So now we will use TensorFlow for our model. So now we have imported all the necessary libraries. These two will be basically for plotting the images. These TensorFlow libraries and Keras libraries will be for our model building and our data and feeding our data to our neural network, and the OS random and shuttle will help us divide the dataset into training and testing directories. So let's run it. So now our session has started. So now we will create testing and validation directories. If you see this error, don't worry, it will not affect our code. So for creation, we will first define a variable which will be slash kaggle slash working slash data. We will first have a folder inside this kaggle slash working, and then inside that data folder we will have every other folder. So now let's define a function: create train val dirs, and we will pass a root path in it. So now we will use our OS module. So OS module has a function named as mkdir. It is make directory function. If any one of you have done some are familiar with the Linux, so you might have heard of this mkdir command in that also. But don't worry if you haven't heard about it. So now we will define our paths. So first we will define our training path. That will be os.path.join the root path and training. Now you might be thinking that I'm just joining the two strings. Yes, I'm doing that, and why I'm using this os.path.join. So I'm doing this um, to basically just not to check these backslashes. Sorry, these front slashes. I don't want to check them. So this os.path.join already takes care of it, and we don't get some random errors that this directory don't exist or this file don't exist, because if you mess up any slash here, this will throw some errors. So it's better to use these functions. Now for cloudy we will have to code this. Sorry, actually these directory names, like that I'm giving cloudy, desert, green area, water, you can name it whatever you want. I'm just naming these like keeping the same names just for the convenience. So it's not like you have to name it certain way. You can name whatever you like. It's just my preference that I like, want to be consistent. So now we have coded all the paths, and now we will just call the os.mkdir function for every path. So now our code is completely executed. Now you can see we have all the directories in place. Okay. So if you this might not load, just refresh it sometimes, because it might take some time depending on your system, depending on your internet connection. So you can see we have 4 directories in training, and same the 4 directories we have in validation. So now let's code our data splitting function. So I will define a function split data. This will take 4 parameters. First of all, source directory path, then training directory, then validation directory path, and then our split size. This split size parameter will control how the data will be divided, like how much data we get in training directory and how much of that will be getting in validation directory. So first of all, we get all the paths for in the source directory. So source files equal to os.list dir source dir. It will list all the files present in a directory. For example, if I pass this satellite images classification slash data slash cloudy, so it will get me all these paths of images, train 10021.jpg and all that in in a list. So now we will get the paths in training. So to copy train, and then we will be using random.sample. So first parameter specifies from which list we need samples, and then how many samples we need. So I will be the way we code it is that split size should be between 0 and 1. It cannot be out of the range, because then this function will throw error. So keep that in mind. Now we will start in source files to copy. So now first we will check whether our file has something in it or not. So we will use os.path.get size, os.path.join source dir comma I. If the file has something, then we will add it in our training directory. So we will use shuttle.copy. So first of all, the first path from which we have to copy, here you can see the source path and then the destination path. So for source path, os.path.join source dir comma I, and then os.path os.path.join training directory comma I. Else, if the file has nothing and it's of 0 size, we will print the file name, print. Let's use file here for more meaning. The I is kind of confusing. So file has 0 size, so ignored. Now we will do the same thing for validation, but now we will do something different. Source, and we will check that this file should not be present in this source files to copy train, because if something is in training directory, we don't want it in test directory. So we'll check if the file not in source files to copy train. If not in, then we will use the same code. Let me copy it for once, and now we will switch this training directory to validation directory. Now we will use these functions to actually transfer our data from this data folder to this working directory. So to start, we will first define our training and validation paths. So training will be equal to slash kaggle slash working slash data slash train, and our validation will be equal to validation. Now we will define our 4 source directories, which will be cloudy, desert, green area, and water. So cloudy source dir, that will be equal to slash satellite image classification, actually wait a minute, that will be kaggle slash input slash satellite image classification slash data slash cloudy. Same thing we will do for rest of the 3 directories. So let's copy it. So that will be for wait a minute, that will be for desert, green area, and water. We will also change this here. Now we will make the paths for validation and training. So we will use cloudy train dir, that will be equal to os.path.join training comma cloudy. That will be the training data. Wait a minute, let me show you. That will be our that will be our training, and then this cloudy folder. Like it still has nothing, but it will have the data when we will execute this cell. So now we will have cloud cloudy valid dir, that will be os.path.join validation and cloudy. Now we will copy these 3 times and we will execute our functions. So split data. First, the source directory. So our source directory will be this cloudy source directory for first. I haven't defined the split size, so let's first define it. Split size will be 0.9. This signifies that I am using 90% of the available data for training and the rest 10% will be for validation. So cloudy source dir, then cloudy train directory, then validation directory, and then our split size. Now copy this function again. Now we will run the firstly this and then this. Now it has thrown error, can't move an online. Oh, actually I haven't done this. This should be an int because length should be an int, so I was wrong in that. Let's see how we got our data or not. So the code has executed. As you can see, we have all the files in training and validation directory. Let me show you validation directory once. So here, see. So 10% of the total data is in validation and rest 90% is in training. So now we will start our image pre-processing. Now for image pre-processing we will use this, wait a second, this image data generator. We are using image data generator because whenever we build a neural network, because we are building a neural network needs equal size images. So it can happen that some of the images are of different size. For example, might has this image is of 2.97 kb and this image is of 9.8 kb. So you can see there are size differences in images. So we don't want that because then we can't feed our images to the neural network. So we will use our image pre-processing to make them of equal size. So now let's start coding. We will define a function. It will take 2 parameters. First of all, training dir and validation dir. Now it is generating data, so train data gen will be equal to image data generator rescale equal to 1 point by 255. Sorry. Then rotation range, that will be 180. Rotation range is in degrees, so it can range from 0 to 180. I am using 180 here. Then uh, width shift range, that how much the image can be shifted or the main subject of the image can be shifted from center. It will be 0.2, that means 20%. Similarly, height shift range, same, 0.2. then horizontal flip, that will be true. Horizontal flip is like uh, um, placing a mirror and getting the mirror image. So it helps us expanding our data set so that we can have features which we might not have in our training dataset but can occur in validation, or if you download any image from the internet and then test the model, um, the feature cannot be present in the model, or model has never seen the feature in training, so that can happen. But yes, these parameters help us to somewhat make our model more robust. And fill mode uh, fill mode will be nearest. One parameter is left. Shear range is like cropping any image randomly, but only 20% of it will be cropped. So now we will generate our data. So training data will be equal to train datagen dot flow from directory. One parameter is directory. We will pass uh, training dir, then target size. I'm taking target size of 100 cross 100. Then what is the class mode? I am taking it categorical. Whenever you are coding for classification problem, like it is a classification problem. Wait a minute. So for classification problem, we always use class mode as categorical. Same thing we will do for validation data generator. Here we will only use one parameter, that is rescale, and validation data will be equal to val datagen dot flow from data, not data frame, directory. First parameter will be directory equal to validation dir, then same target size should always be same whenever you use it, because then again it will throw errors. Class mode will be categorical, and then return both training data and validation data. Let's run it. What happened? Now we will use this function to get our training and validation data. So we will use train generator and validation generator. That will be equal to, or wait a minute, train val generators. We will pass these variables, training and validation, these. Now let's run it. It has shown an error. Oh, I created a typo here. So Here you can see we have found 5067 images in training data generator, and for validation we have 564 images. It also shows you the four classes. Again, that only happened because how we set our directory structure. If it will be different, then it could have been thrown some errors, because what happens is that these training uh, and validation generators are using image data generator, which uses directory name in which you have images as a label for those images. So keep that in mind whenever you are using image data generator. Do take time to think how you are going to structure your folder structure. So now we will visualize our images. For visualization, I will define two arrays. One is xtrain and other is ytrain. So we will traverse for c equal to 0 for feature comma label in train generator. So we will append feature in xtrain, label in ytrain, and then we will do C++. I only wanted this to run once, so again you can get as many images as you want. Wait a minute. V dot array. So now we will transform our xtrain into a numpy array. Here you can see it is saying 1 comma 32 comma 100 comma 100 comma 3. Now you can say that yes, 100 comma 100 comma 3 is okay. That's our image, because we are using 3 bytes for our color, and 100 cross 100 is the image size we set up earlier. So you can change it, but I am keeping it 100 cross 100. Now where does the 32 come from? Actually what happens is that we make batches of images. Not we, but this image data generator make batches. So you can here, when you're using flow from directory function, you can define a parameter known as batch size. Again, I'm not defining, so it has a default value of 32, which is showing here. Again, you can change it, you can set it to 16, even you can set it to 1. But yes, you have to experiment it, because batch size matters, and it also improves or can improve your model performance. So do consider this parameter too. But for now we have 32 images. So first we will travel those images xtrain dot travel, or you can use reshape. I'm preferring the reshape function, so np dot reshape, because now I know the shape. Xtrain comma, now what will be the shape? 32 comma 100 comma 100 comma 3. And you can also print the shape of xtrain again to see your function worked or not. See, the function worked. Now we have numpy arrays for plotting. Now we can see the plotting function. So for plotting we will use fig comma ax equal to plt dot subplots. Now how many subplots I need? So we will define the parameter, and fig size I am taking, you can take it anything, I just wanted to take it 30 into 30. So now we will plot the first 16 images for I in range 0 comma 16 ax int I by 4 comma I mod 4 dot I am show. Because we are working with images, so we will be using I am show xtrain I, and then lastly plt dot show. Now you can see the first 16 images of xtrain. Again, there are some cloudy images, some images of deserts, and some of green area, maybe that signifies forests or any green area it can be. So now we have pre-processed our data and we have also completed the data visualization. Now we can move on to model creation. So let's start creating our model. We'll use function, create a function, create model function, which will take no parameters. So model will be equal to keras dot models dot sequential. So first layers dot conf 2d. So 32 convolutions and convolution size will be 2 cross 2. Activation will be value. Input shape is 100 cross 100 cross 3. Then we will use a max pooling layer. Max pooling 2D. That will be a 2 cross 2 layer. Then we will define two more layers which will be same but just the convolutions are different. So apart from 32 we will use 64 convolutions. Again you can change these numbers however you like, and I will encourage you to experiment with these numbers. Then we will use layers dot flatten, layers dot dropout, dropout 0.1. It means we are dropping 10% of the neurons. Sometimes this works, sometimes this does not. So what it does is it drops 10% of neurons, because sometimes it happens that we have multiple neurons of same weight, like multiple neighboring neurons of same weight, which can affect our model performance, because most of the times our model is making predictions, so it will be like guessing how probable a particular thing is to have. For example, a image. Let me give you an example. For example, this desert image. It can say that yes, I'm thinking that 50% chances are this is a desert image, then 25% chances that it is a water image, then green area, and like so on. It will have probabilities which will all add up to 1, and we are taking the maximum probability, that maximum what it thinks is true. So sometimes it happens that when you have multiple neurons of same weight, especially neighboring neurons, the prediction can go wrong. And then lastly, there's dot dense for activation softmax. Then we will compile our model, model.compile. Again, the compilation will happen. In this, we will define the optimizer we will be using. Optimizer. I'm using Atom optimizer. You can use any other optimizer you like. Loss. I'm using categorical cross entropy. Categorical cross entropy. Categorical cross entropy, and the metric on which we are judging it is accuracy. Then we will return the model. Now we will use this function model equal to create model, and then history equal to model dot fit train name train generator. How many epochs we will use? I'm using 11 epochs. Then verbose is 1. Validation data will be our validation generator. Let me check or validation generator or something else. Yes, it was validation generator. So now let's run the functions. Now here you can see it has started running. Wait a minute, let me do that. So now it will take some time, and it will run for 11 epochs. Again, you can see here, that's an interesting thing. Here it is written 159, but we are training on how many images? 5000 the something images. To be exact, 5067 images. So what happens is that it groups the images into batches of 32. So uh, at one time it will train with a batch of 32 images, then next batch of 32 images, and it will work that way. So here you can see the first epoch is complete. Here the loss will be there, and the accuracy on the training data, and then on the testing data for each epoch. Now the training is complete, and you can see at the end of 11th epoch we have a training accuracy of 92.13% and a validation accuracy of 92.73%. This is a very good accuracy. Yes, it can be better, but the point here I'm stressing on is that our model's training accuracy and the validation accuracy is more or less same, which is a very good sign that our model is not overfitting. Because what will happen in overfitting, that it will perform great on our training set, but in validation set the accuracy will be very poor. So here it is almost like close, where validation accuracy is somewhat higher than the normal, but yes, it is close. So that's the thing. We are not overfitting in our model, which is a good sign. Now we will plot the training and validation accuracies in a graph so that you can see how you can get a visual of this data, because dealing with numbers is kind of difficult and dealing with images is kind of easy for our eyes. So let's start. So we will take four variables. Dot. First we are taking the loss from history object, then accuracy. Let's just define it as ACC. History dot history accuracy, then val loss, validation loss. This will be history dot history val loss, and then validation accuracy, which will be history dot history val accuracy. Now we will plot the accuracies and the losses in two different plots. We will first get the x-axis, which will be epochs equal to range of length of the accuracy array. It will be a list, so we are using range from 0 to the length of the accuracy list. Then we will plot uh, epochs accuracy, color will be red, Then we will plot the same epochs, but now we will have validation accuracy here, and I am using blue color. Then plt.x label, that will be epochs. Then plt.y label, that will be accuracy. Then plt.legend, it will be training, validation, and then plt.show. Now let's run it again, and here you can see we have our accuracy, which is plotted against the epochs, and here we have our legend. So red line is showing the training and validation. You can see some in between the epochs the validation accuracy dropped, but again it is close to our training accuracy. Same graph we will plot for the losses. So plt.plot, now we will use the loss, sorry, first parameter will always be epochs, then loss, then r, because that's training, then epochs val loss, then plt dot x label will be epochs, then plt dot y label will be the loss itself, then same plt dot legend and plt dot show. Let me copy it because it's same. Now we will run it. Now both of our graphs are plotted. So here you can see the accuracy plot, and here we have, wait a minute, the loss plot. The losses are also decreasing as the epochs pass, and the accuracy is increasing, which is what we want. So our model is complete. Thank you for watching the video. If you like this video, please do share, subscribe, and like this video, and the code will be shared with you in the description on Kaggle. So if you like my Kaggle notebook, please give it an upvote. Thank you very much for watching my video.